Okay, thank you. Today I have the pleasure to introduce Marcus and Teagan. Marcus holds a PhD degree from McGill University and now works as a researcher at CSIRO. His work focused on basin analysis of sedimentary and weakly metamorphosed sedimentary successions, gathering facies analysis, sequence stratigraphy, chemo and tectonostratigraphy, and isotope geochemistry to improve the mineral exploration programs and help to develop targeting concepts. The projects where he works usually involve the collaboration with structural geologists and geophysicists. Besides mineral system science, he also is interested in Proterozoic Earth history, with some ongoing international collaborations in the co-evolution of atmospheric oxygen and life. Our second speaker, Teagan, holds a PhD from Monash University, where she investigates the geophysical modeling techniques to understand volcanic systems. Few years ago, she joined CSIRO, first as a postdoc, and now is the Basin's team leader, where she used their strong geophysical skills to improve the knowledge and targeting mineral deposits. Today, Marcus and Teagan together will present the implication of their geophysical and sequence stratigraphy for targeting concepts of clastic-dominated type in McArthur Basin, which is one of the most endowed zinc-lead regions in the world. Marcus and Teagan, the next 15 minutes or so are yours, and I'm really looking forward to hear what you have to say.
Thank you, Filipa, for that introduction. So my name's Teagan Blaikie, and I'll be starting off the presentation today, talking about some of the geophysical modelling work that I've done, and then I'll hand over to Marcus in the second half of the presentation to talk about the sequence stratigraphy and targeting of zinc-lead deposits in the McArthur Basin. So just to start off with some acknowledgements, this work was part of a 3-year project that was part of a much broader collaborative initiative between the CSIRO and the Northern Territory Geological Survey. And this project has involved multidisciplinary research involving geophysics, sedimentology and sequence stratigraphy, geochemical characterization of the McArthur Group sediment-hosted zinc-lead ore deposit, and numerical simulations of fluid flow. I'd like to acknowledge the input into this work provided by the McArthur Basin team at CSIRO. That includes Peter Schaubs, Sam Spinks, Susanna Smith, Heather Sheldon and Tim Monday, and also input into this work by our collaborators at the Northern Territory Geological Survey. So as I mentioned, this work presents results from a multidisciplinary approach into basin analysis, with a real focus on understanding how these different aspects of the mineral system have come together to form a deposit. And some of the work I'll be talking about focuses on the large-scale structural architecture of the basin and some potential fluid pathways. We'll also be looking at the structural controls on sub-basin development. Marcus will focus a bit more on the sedimentology and sequence stratigraphy and the formation of suitable trap sites for metals. So you have a schematic on the right-hand side here, just showing sort of the different aspects of the system we're looking at, starting off with the broad scale fault architecture and then looking at more detail at sub-basins and traps. We don't really, our work hasn't particularly focused on the source of potential metals to form a deposit. We do sort of speculate a little bit on this based on the geophysics, but that's not something we've focused heavily on in this work. So just a regional overview of the McArthur Basin. It's located in Northern Australia and is part of an extensive basin system that covered large areas of the North and South Australian Craton during the Paleo to Mesoproterozoic. The basin developed in a far-field continental back-arc setting and was influenced by events occurring along the plate margins. So it had a long-lived subduction zone at the southern margin of the continent and then rifting and development of the passive margin at the east of the Craton. So in the Northern Territory, the McArthur Basin is exposed in the northeast up here. It extends undercover to the west underneath the Beetaloo Sub-basin and connects with the Birrindudu Basin in the west. And it's connects to equivalent sequences in the Mount Isa Basin to the southeast. The McArthur Basin has had a long-lived and complex evolution, and as I mentioned, it's really been affected by plate boundary processes which have caused transient episodes of extension and basin inversion. As a result of this, the basin has developed quite a complex architecture of large basin scale normal and strike slip faults, which are periodically reactivated during different phases of the basin's histories, and in some cases, these faults became conduits for mineralizing fluids. Structurally, the basin is comprised of two north trending fault zones. So these are the Batten and the Walker fault zone, separated by the east-west trending Europunga fault zone. The work we're focusing on today focuses on the Batten fault zone and the southern McArthur Basin. So together with equivalent successions in Mount Isa, this region forms one of the largest zinc provinces on Earth. And mineralisation in this region tends to be hosted in structurally controlled sub-basins, similar to what I've shown in this figure on the right-hand side here. And one of the challenges with exploration in this area is that many of the faults controlling sub-basin growth and deposition of prospective stratigraphy are blind at the surface. They have quite a large offset at depth, but only minimal offset through younger stratigraphy, which has made recognising these structures during routine mapping really challenging. So this project has applied geophysical interpretation and modelling at a range of scales to understand the really broad scale structural architecture of the basin, try and understand fault overprinting relationships and sub-basin development. And this is linked with the sequence stratigraphic work that Marcus will talk about in the second half of this talk. So the stratigraphy of the basin is divided into 4 unconformity-bound depositional sequences, being the Tawallah Group, the McArthur Group, the Nathan Group, and the Roper Group. And this is the stratigraphy as is seen in the southern McArthur Basin and the Batten Fault Zone. So the oldest group comprises the Tawallah Group, deposited predominantly under extensional conditions, and these comprise sandstones, conglomerates, volcanics, and minor carbonates. And the volcanics in this unit have been interpreted as a source of metals for mineralisation. The overlying McArthur Group comprises carbonates, mudstones, and sandstones, and it is host to the Barney Creek Formation, which is the important unit hosting mineralisation. This is overlain by the Nathan Group, comprising siliciclastics, carbonate rocks, and minor intercalated mafic volcanics. And this is overlain by a laterally continuous siliciclastic succession known as the Roper Group. So geophysical data can inform on the 2D mappable and 3D subsurface extent of geophysical features. And we're really quite fortunate in this area because we've got some really great geophysical data sets. And this has been a really good tool to support regional structural analysis in this area where parts of it are reasonably well exposed and other parts are undercover. So it's been a really great tool to sort of support regional interpretation of the structural architecture of the basin. So what my work has involved is the interpretation of gravity, magnetic, radiometric, and a little bit of AEM data across the Batten Fault Zone. And I've done some forward modelling of the gravity and magnetic data co-located with some deep seismic reflection data where available. And the work has been focused on both a regional and a local scale to understand both broad scale basin architecture and sub-basin development. So this is, these interpretations are integrated with previously mapped geological and structural data across the basin and have been tied in with some of the sequence stratigraphy analysis from drill cores across the basin, which Marcus has been working on. So this is an example of some of the geophysical data sets that I've interpreted. So we've got the first vertical derivative of the Bugey gravity data on the left and the reduced to pole magnetic data just overlaid on a first vertical derivative on the right-hand side. So some of the key features of this data set I'll point out is this north trending gravity high. So this corresponds to the largely the McArthur Group, where the sort of thick carbonate sequences within that group are denser than the surrounding siliciclastic sequences of the overlying Roper and underlying Tawallah Group. We also see some gravity highs related to thicker sequences of volcanics within the Tawallah Group. We sort of get a lot of structure through here. So the resolution of this data set varies between 2 and 4 kilometres, with some 500 metre profiles that are located in here as well. In some parts, we're almost able just to map different stratigraphic layers within the McArthur Group where we have really high resolution data. On the right-hand side here, we've got the magnetics, and I'll just point out, you can see this sort of high frequency stipple texture, which is quite characteristic of volcanics. As this texture becomes more and more subdued, it indicates that the volcanics are becoming deeper and deeper, and they're overlaid by the McArthur Group, which is essentially non-magnetic and is transparent to the magnetic data. So looking at how attenuated these volcanics gives us an indication of how thick the overlying McArthur Group can be. And you can also start to see some structures coming through here, these lineaments that are cross-cutting this texture of the volcanics. So these are all the faults that we've been mapping and trying to understand the overprinting relationships of. So this is just an inset of some data just located in the north of the Batten fault zone here. And this just highlights some of the key fault overprinting relationships that we've observed in this area. So label number 1, we've got some northwest trending faults. These tend to be quite a prominent structure across the entire McArthur Basin, and they're one of the earliest I guess fault orientations, and they tend to be overprinted by pretty much every other fault orientation that we see. So here you can see the northwest trending faults overprinted by some north-northeast trending faults. If you follow these northeast trending faults down, they are truncated by these north-northwest trending. These are thrust faults coming down through this part of the basin. Also got the EMU fault, which is quite a important slip structure running through the EMU fault zone. And you can see them also truncating and overprinting these north-northeast trending faults. Here at the label 4, we've got some northeast trending faults. These have an interpreted normal sense of movement. You can see the subdued magnetic texture on either side of the faults, indicating sort of downward movement of those volcanics. And here we have at number 5, northwest trending faults, which are just slightly offsetting some of these northeast trending faults, which is interpreted as just reactivation of these during sort of later deformation. So based on that structural interpretation and some of the sort of key geophysical textures I pointed out in the previous slide, what I've done is produced a solid geological and structural map which shows the distribution of proterozoic stratigraphy undercover. So this is taken from mapped outcrop, and also its interpreted extent undercover by correlation of its geophysical signal. And so what this map sort of highlights on the left is the distribution of each of the different depositional packages of the McArthur Basin, and this is divided at the subgroup level. And on the right-hand side, we've got a really high resolution map of the stratigraphy down to formation level. So this is all the geology that's just immediately underlying the undercover. And this is important for understanding where prospective stratigraphy may still be preserved. So some of the modelling I've done as part of a geophysical survey acquired by the Northern Territory Geological Survey back in 2017, we acquired some 500 metre gravity profiles along each of these red lines indicated here. And this was to support forward modelling to try and understand the structural architecture of the basin. So we constructed 6 east-west and 1 north-south regional scale cross-section. These were modelled against the gravity and the magnetic data. And these models were constrained by the structural and lithological interpretation I just presented. In some cases, you can see these dashed lines represent some seismic data. So where we've had coincident or seismic data located into a section the architecture determined from the seismic data was used to constrain the models. We've had some well data, which we've incorporated as well, and as well as with the Northern Territory survey has quite a comprehensive rock property data set that was also used to constrain modelling. So we've taken weighted averages from measurements taken from each formation. Because these are quite broad scale models, we've had to we're modelling at the scale of each group. So we've taken weighted averages to determine an approximate density and magnetic susceptibility properties to apply to each region of the model. So here is one of the models located in the central Batten fault zone. So profile B, just showing here, got a deep seismic reflection profile located just to the north of the section, just following my pointer here. So the architecture doesn't match exactly because it's a little bit to the north, but it was sort of used to constrain the geometry of aspects of the model. So up the top here, we've just got the geology, solid geology interpretation. This top panel here shows the magnetic data. So the black dots show the observed data. The black line is the model data and the red is the error. And here we have the gravity data as well. Panel D, this is the cross section that we've modeled. So this is just showing the present day architecture of the Batten fault zone. You can see you've got the McArthur Group in orange, the Tawallah Group in yellow. And I'll just point out a few key features of this model. So we can see here we've got a thick sequence of the McArthur Group preserved in the central Batten fault zone. We've got the EMI fault zone, which is quite a prominent strike slip structure. Underneath this, we've got a sort of fairly thick sequence of the Tawallah Group. In order to reconcile this gravity anomaly here, we've had to introduce some mafic volcanics within this sequence. And there's sort of hints, potential hints of this in these mafics in the seismic data as well. You can see we've got this west dipping thrust fault known as the Tawallah fault. So this is sort of showing some later movement along this structure that's post-dating deposition of these sequences. But what we do see is some thinning of the Tawallah Group on the western side of this fault, which indicates that there was potentially uplift and erosion along this structure prior to deposition of the overlying McArthur Group. So this is another section, section D, just located to the south of this to the previous model I showed. Again, what we're seeing is some volcanics which have been introduced to try and reconcile some of these gravity and magnetic anomalies within the Tawallah Group. We can see the present faulted and slightly folded architecture of the basin. We have a gravity and magnetic low feature here, which is interpreted as potentially a granite intrusive in the basin. We're not really sure of the timing of this structure, but we do need sort of a low density body in there to try and reconcile this anomaly. Again, just seeing some thinning of the Tawallah Group's stratigraphy as we move across to the western side of the Tawallah fault. And we're starting to transition into the Beetaloo Sub-basin here, so we're starting to get quite thick. Sequences of the Roper Group with the Beetaloo Basin forming sort of the main deposit center for that particular depositional package. This section here represents a north-south cross-section through the central Batten fault zone. I can see sort of this broadly folded architecture of the Batten fault zone. Here we can see we've got some east-west faults running through the central Batten fault zone here. And we can just see some thickening of the Tawallah Group stratigraphy and also the McArthur Group stratigraphy against these east-west faults. So these are interpreted as growth faults that were potentially active during deposition of both the Tawallah and the McArthur Group. Again, we're getting these volcanics in here to try and reconcile some of these gravity gravity anomalies. And this part of the section is constrained by some seismic data as well. And finally, just another section located in the north of the profiles, in the north of the Batten fault zone. So this area has seen, I guess, a lot more faulting and uplift, exposing parts of the Tawallah Group, so the oldest part of the stratigraphy in the north of the fault zone. So you can see we've got lots of thrust faults uplifting that stratigraphy there. What we see here, shift from, this is their EMU fault zone. In the previous models, we've had the thicker parts of the McArthur Group deposited on the western side of the EMU fault, and then as we go into this northern profile, we see the thick sequences of McArthur Group preserved on the eastern side of the EMU fault. So this here just is a schematic of all those. I only showed 4 there, but we've produced 7 sections. So this is just a representation of those in 3D with just some surfaces showing some of the major structures. So we can see this star here represents the McArthur River lead zinc deposit, and you can see they're quite proximal to where we're modelling these thick volcanic sequences. And here on the right-hand side is just a, I guess, an inset of the central Batten fault zone, just showing some of the major faults that we've interpreted and some surfaces representing the base of each of the major depositional packages. So based on those modelling results and also observations from the solid geology and structural interpretation and previous geological work in this part of the basin, we've compiled some fault event maps for this part of the basin for sort of different extensional and deformation events. In the early Tawallah Group, we've had an initial period of extension, the modelling showing thickening of stratigraphy against sort of the northwest, southeast and north-south structures. It's also thicker in the east, especially in, I guess, northwest trending gravity lows. So I might just flick back to this section here where I can see thickening of the Tawallah Group heading out towards the east. So that's sort of trending into a northwest gravity low, potentially indicating half-carbon development earlier in the basin's history. We've had a mid-basin inversion event causing uplift and erosion of stratigraphy, and I pointed out thinning of the Tawallah Group adjacent to the Tawallah fault, which has just been shown here. We then had renewed extension and further deposition of the siliciclastic sediments. So for the McArthur Group, we've had largely sort of a sag phase of sedimentation with intermittent periods of extension around sort of 1645 to 1640. During this sort of period of extension, we've seen a lot of strike slip faulting and growth faulting along sort of these east-west, east-north trending faults in the central Batten fault zone. And we do see thickening against parts of the EMU fault in sort of elongate some basins as well. Overall, we see thinning of the McArthur Group towards the west and towards the east. This has been followed by deformation related to the orogeny, which is partly responsible for some of the sort of the related faulted architecture that we're seeing in the models in that broad scale folding. I haven't shown, since I guess it's not overly relevant to what we're talking about today, but there are some later extensional and deformation events that have followed what I've shown here today. And so happy to talk about those later if you're interested. So based on those interpretations, the interpretation of the geophysics has really helped refine the fault architecture across the broader Batten fault zone in the southern McArthur Basin, but also in much higher resolution in the central Batten fault zone. And this is where we see the McArthur River and other mineral deposits, other lead zinc mineral deposits forming. And what we're seeing based on the structural interpretations is two styles of subbasins forming. And the first type are bound by the north-northwest trending EMU fault zone, where we see these elongate sort of pull apart basins between segments of the strike slip faults. An example of this is the Glide and Karambarini subbasins. And the other type we see is adjacent to these east-west trending normal faults I pointed out during modelling. And this is where we're seeing the second type of subbasin. So the scale of the regional models I talked about was really was not appropriate to resolve the architecture of these subbasins in great detail, which occur at more sort of the 1 to 10 kilometre scale. So we've had a look at some high resolution case studies to try and understand the architecture of these subbasins in more detail. So the first type, showing sort of these subbasins forming, these transtensonal subbasins forming between strike slip segments of the EMU fault zone. So this is an example of the Glide subbasin, which is a structurally controlled, concealed subbasin. It lies under a few tens to hundreds of metres of cover. It preserves up to 900 metres of the Barney Creek Formation, which is known to host mineralisation within the McArthur Basin. Has previously been interpreted as a transtensional negative layer structure. So this particular subbasin has quite good data coverage. We've got some Falcon airborne gravity gradiometry applied at 400 metre line spacing by energy. There's also some airborne EM at 1 kilometre line spacing and quite a number of drill holes through here to actually constrain modelling. So this figures here shows the structural interpretations and some sections that I've modelled. So here we've got the gravity data. I've got the broader scale architecture constrained from the large scale models that I just presented. And here we can see some smaller growth faults located within the, reserved within the McArthur Group, controlling thickening of the Barney Creek Formation towards the EMU fault zone. Here we're showing some of those airborne EM sections where we've got this conductive anomaly that's coincident with the Barney Creek Formation, and we're seeing thickening of this conductor towards the EMU fault zone, which is consistent with what Marcus has also logged in drill cores in this part of the basin. Second type of subbasin are those bound by these sort of east-west to east-northeast trending normal faults within the central Batten fault zone. So here's an example from the Myrtle subbasin located approximately 20 kilometres southwest of McArthur River. It's imaged by the same gravity gradiometry data that the Glide subbasin was. So here's just another forward model across this section here through the subbasin. We've got the stratigraphy is constrained by 2 drill holes, and we can see it's sort of quite a compartmentalised subbasin, probably a lot more complex than initially thought. And we're seeing sort of two main depicenters in here corresponding to these little gravity lows here. So it looks like in this case, drilling has missed the main depicenter of the subbasin. It's just, I guess, a comment on the source and transport of metals. So I pointed out in some of these models that we're seeing some mafic volcanics, so we're having to put these in here to reconcile some of the gravity and the magnetic anomalies that we're observing. So the models are suggesting that these volcanics are anonymously thick in this part of the basin. And equivalent units that are exposed across the basin have been shown to have undergone potassic alteration and are depleted in base metals. And these volcanics have traditionally been interpreted as the source of metals for mineralisation. So having quite a thick sequence, quite proximal to where there's no mineralisation, And we're also seeing some of the major sub-basin bounding faults actually tap these volcanics and also aquifers within the Tawallah Group. What we're also seeing in some of the models is felsic intrusions within the basin. There are granitic clasts known within some of the sandstone units of the Tawallah Group, which may be derived from some of these intrusions, and that may represent a potential another source of metals in this region. So just in summary, we're seeing or interpreting extension and sub-basin development during deposition of the Barney Creek Formation. Interpreting this under broadly north-south directed extension, and we're seeing the development of these elliptically shaped sub-basins developed along strike-slip segments of the EMI fault zones. This is just a schematic of how we picture the basin at the time of deposition of the Barney Creek Formation. And so these sub-basins along strike of the EMI fault tend to preserve the thicker sequences of the Barney Creek Formation. We also see growth on inherited east-west normal faults in the central Batten fault zone. So mineralisation in the Barney Creek tends to be associated with the presence of these east-west oriented cross faults and also proximal to the thick mafic volcanics that we recognise during regional scale modelling. So I'm now just going to hand over to Marcus, who's going to talk about developing a stratigraphic targeting concept for the host.
Thank you, Teagan, and hello everyone. I'm Marcus. And we are now going to change the scale of our investigation and zoom in a little bit. Teagan used different geophysical data sets to reconstruct the tectonic history of the southern McArthur Basin. And this helps to understand different types of sub-basins. And it also helps to get a better handle on potential fluid flow pathways. We are now going to use Facies analysis and sequence stratigraphy to first identify which lithofacies would represent the most suitable chemical trap for oxidized base metal brines. And then we are going to use sequence stratigraphy to start predicting where in the basin this most suitable chemical trap should occur. This means we're going to develop a conceptual targeting concept for McArthur River style mineralization by reconstructing the stratigraphic architecture of the host unit, which is the Barney Creek Formation. And we have studied the Barney Creek Formation in 12 drill cores, which are shown by these white circles here, overlain on the reduced to pole magnetics map of the Batten fault zone, the Teagan already showed. You can see we've got a fairly nice north to south coverage, complemented by a couple shorter west to east transects. And I have logged all these drill cores at a decimeter scale resolution, together about 7 kilometers of drill core. And all these drill cores intersect the 1640-million-year-old Barney Creek Formation, which is the host to all known economic rate mineralization. However, I have also included the underlying and the overlying stratigraphic units in my investigation, if they were in fact intersected by the exploration drill cores, simply because together this entire succession will be much more informative than the Barney Creek Formation alone. And the first thing that we have to do when we want to develop a targeting concept based on sedimentology and stratigraphy is a detailed facies analysis. This means we have to reconstruct all the different depositional environments that existed in this basin at the time. And we do this by looking at the composition of the sedimentary rocks, as well as the preserved sedimentary textures and sedimentary structures. And we did this, and we were able to distinguish 19 different lithofacies types, 19 different deposition environments, which we grouped into 4 facies associations. So deposition environments or lithofacies grouped into the same facies association basically represents the same relationship to water depth. And we can distinguish upper intertidal to continental environments, shallow subtidal to intertidal environments, as well as subtidal to shallow subtidal and offshore to offshore transition deposition environments. And I want to show you at least one lithofacies example for each facies association. So here we've got a red mud rock with centimeter scale anhydrite clasts or nodules formed in the supratidal subcar environment. And those are environments we know, for example, from the Persian Gulf Coast today. This here is a microbial laminite with little crinkly microbial laminae, which represents low energy intertidal to shallow subtidal deposition environments, as we know them, for example, from Shark Bay here in Western Australia. This here is an oorite grainstone with little concentric oorites and centimeter scale intraclasts. And this lithofacies represents deposition under highly energetic shallow marine environments. Today, those environments, for example, are found on the Bahama banks. And this here at the end is a carbonate turbidite deposit formed below storm wave base on a slope. This here has a nice slump fold, and this lighter brown or gray layer, laminae, is actually thin sedimentary pyrite. So these are just 4 examples, but you probably get a feeling for the rocks now. And when we reconstruct all these 19 different lithofacies types and deposition environments, we can start to put them together in a facies diagram, which looks like this. So this here is not a basin reconstruction. It doesn't have a north arrow and it doesn't have a proper scale. It is rather a classic way in sedimentary geology to show how all these different lithofacies types and deposition environments that we identified relate to each other. So for example, starting at the base of our studied stratigraphic succession is the Myrtle Shale, and the Myrtle Shale represents classic upper intertidal mudflat to supratidal subcar environments. And is dominated by these red mud rocks with anhydrite nodules that we just saw, and sometimes has lenticular bedding with isolated sand ripple trains. Many carbonates, for example, from the Amaruga and Tina dolostones, are comparable to modern day carbonates that form in peritidal environments. That means environments that form around the tides. For example, pond and channel belts as we know them from Andros Island on the Bahamas today. And classic lithofacies are these mud-cracked microbial laminites that we just saw on the previous slide, as well as carbonate muds with fenestra. Then moving up the stratigraphy, we know at Barney Creek times, the basin was highly compartmentalized in paleohyes and subbasins. Here's a zoom in the close-up. And the classic Barney Creek formation is dominated by these dolomitic siltstones that were deposited by turbidity currents in subbasins. However, it also comprises organic carbon-rich and pyritic black shales, as well as carbonate grain flow deposits and carbonate debris flow deposits. So now we may ask, why do we actually do such a detailed sedimentological analysis and reconstruct all these different deposition environments? And the question is actually quite simple. We want to know which lithofacies would represent the most suitable chemical trap for an oxidized base metal brine. So we probably want organic carbon as a reductant. We probably want sedimentary pyrite as a sulfur source. And if the fluid was acidic, we probably want some carbonate content to bring up the pH. And all these would basically cause chemical reactions that would cause base metal sulfides to precipitate, and that would form mineralization. So considering this, we can say the organic carbon-rich black shales and pyritic black shales are the most suitable chemical trap, but it could also be the dolomitic siltstone if it is organic carbon-rich and pyritic, as it is in some places, in some stratigraphic intervals. In other places, it's more carbonate-rich. So now we understand which lithofacies might be interesting to target. And we need to come to the second point, which is how can we start predicting where these lithofacies may occur? So we need to start working with fence diagrams with stratigraphic transects. And this here is a transect that I will be showing throughout this presentation. It is from the southernmost part of our study area, about 50 to 70 kilometers to the south of McArthur River, and it collects the drill core Lamont Pass 3 in the north, this one here, with drill core GR11 in the south, this drill core here, and basically connects all these red marked drill cores. So this here are my detailed lithofacies logs. Next to them, carbon isotope chemostratigraphic plots. And in this case here, also a downhole gamma ray log. In this drill core here, Lamont Pass 3, the Barney Creek formation is about 200 meters thick, not quite, but about 200 meters. And as we step across this fault here, which is this fault, and go into the sub-basin, pretty much all of this is Barney Creek formation, and it thickens to about 900 meters. So we've got significant thickening of the formation from almost 200 to about 900 meters of stratigraphy. And importantly, this lower interval here, this here, which is called the HYC pyritic shale member and hosts the McArthur River and Tina deposits, also shows thickening as we step across this fault and go from paleo-high into the sub-basin. So these different colors here represent our facies associations now. And we can put them in our transect and understand how they are distributed along this transect. We can see that in the sub-basin, most of the Barney Creek Formation comprises these offshore transition to offshore lithofacies, mostly turbidite deposits, deposited below storm wave base or just slightly above storm wave base. In contrast, on the paleo high, it looks like only the lower half of the Barney Creek Formation really represents those offshore facies, whereas the upper part are more platformal and shallow marine carbonate environments. So we start to understand something about the sedimentology and stratigraphy, and this brings us back to our facies analysis and the idea, what lithofacies do we really want to target for mineralization? And keep in mind, we wanted organic carbon and we wanted pyrite, these black shales and bituminous dolomitic siltstones. And those two will mostly be associated with the thick succession of offshore and offshore transition facies in the sub-basin. This is nice, but that's not good enough for targeting, because if we really want to understand where those lithofacies should occur, we need to understand the processes that lead to their deposition. And this means we need to reconstruct the stratigraphic architecture and evolution of the Barney Creek Formation as a host unit. And this is something that we do with sequence stratigraphy. So what is sequence stratigraphy? And I will keep it very, very brief. Sequence stratigraphy identifies cyclicity in the stratigraphic record. This cyclicity is a result of the interplay of sediment supply. How much sediment do I bring into the basin? And accommodation space. How much space is there for my sediments to fill? And this interplay will cause shoreline shifts. The shoreline will prograde into the basin, and it can also backstep and move back towards the continent. And these shoreline shifts will cause certain sequence stratigraphic surfaces to form. And some of them are timelines. That means if I identify them in my drill cores or outcrop sections, I can precisely correlate from section to section or drill core to drill core, whatever I have. And I'm now going to show you two animations that will hopefully help to understand how we can use sequence stratigraphy to predict and understand where those most potential chemical trap lithofacies should occur. So the upper animation shows us the shift of deposition environments and the shoreline, which is this point here, into the basin. And then the deposition environments move back towards the continent and prograde again. Important for us is this dark blue lithofacies, which are deep marine environments, and those are often the most organic carbon rich and pyritic facies. And of particular importance is going to be the maximum flooding surface, which is going to form shortly right now, this blue line here, which represents the most landward retreat of the shoreline. This is usually the most pyritic and organic carbon-rich interval in our stratigraphic succession. And this maximum flooding surface is a timeline. So we can precisely correlate it from drill core to drill core. And this means we can now start to understand where those chemical trap facies may occur. Then at the bottom here, it's the same simplified shelf to slope transect. But those colors now represent systems tracts that together make up one sequence. We've got a high stand systems tract. The shoreline moves in towards the basin. Now we drop the sea level. We've got a falling stage systems tract. Shallow marine environments were eroded. And the blue now is a transgressive systems tract that brings this chemical trap facies across the study area, culminating in this maximum flooding surface. Shifts and how they will influence the deposition of suitable chemical trap facies in mind, we can now basically replace this interpretation of facies distribution by a sequence stratigraphic interpretation. So this is the same transect. The Barney Creek Formation, this interval here, is comprises two sequences, which we call B1 and B2. These colors here are the systems tracts again that together make up one sequence. And they are the same colors as you just saw in the bottom animation on the previous slide. So sequence B1 starts with a low stand systems tract shown in yellow here. And in this case, those are shallow marine carbonate environments that prograded towards the basin. This is followed by a transgressive systems tract shown in blue here, which records significant backstepping of the shoreline and transgression. And it records deposition of highly organic carbon-rich and pyritic dolomitic siltstones. The transgression culminated in the maximum flooding surface, the blue dashed line here, which is a timeline again, right? And we can use it for correlation And this maximum flooding surface is usually developed as an organic carbon-rich dolomitic siltstone on paleohighs and in sub-basin margin areas. However, it can be developed as an organic carbon-rich black shale and fairly pyritic black shale in sub-basin depot centers. Then this is followed by, shown in green, a thick high-stand system tract. Mostly this composes turbidite deposits, which become gradually more carbonate-rich upsection. And at the top of the sequence B1, we've got this falling stage systems tract, meaning the relative sea level dropped sharply, shallow marine carbonate environments were eroded, and this carbonate material was then redeposited as carbonate grain flow and debris flow deposits shown in blue here in the lithofacies log into the sub-basin. Just very briefly, sequence B2 starts with a thick low-stand systems tracts, so mostly carbonate-dominated turbidites that were deposited in the basin. It's very thin on the paleohigh. We've got major backstepping of the shoreline. Organic carbon-rich pyritic facies is being deposited, and this culminates in the maximum flooding surface, followed by high-stand deposition again. So this area here is truncated by the sub-neoproterozoic unconformity, shown by the little wiggly line here. However, on the paleohigh, in this area here, Namon Pass 3, the overlying units are preserved. So now we understand facies distribution and stratigraphic architecture. That means we start to be in a position where we can predict where the most interesting lithofacies to target should occur, because we understand the processes of shoreline shifts and how this process will basically lead to the deposition of the desired lithofacies. Remember, it's organic carbon, it's pyrite we are after. So it turns out that the Barney Creek Formation is fairly organic carbon rich and pyritic throughout, but it is in particular the transgressive systems tracts, the blue intervals here, that are the richest in organic carbon and pyrite, and in particular the maximum flooding surfaces, which again can be developed as a highly pyritic and organic matter-rich black shale. And this transgressive systems tracts here more or less corresponds to the HYC pyritic shale member, and the McArthur River and the Tino deposits sit stratigraphically within this transgressive systems tract. So we can now take all this information and make it a bit simpler and try to conceptualize this. So this here is a conceptual model or sketch of a paleohigh and a sub-basin. This here are 100 meters of vertical scale, and this is 1 kilometer of horizontal scale. The sequence stratigraphy is now shown in a simplified way by these triangles here. Fill triangle means transgressive systems tract, and empty triangle means we lump together all the regressive deposits, high stand, falling stage systems tract, and low stand systems tract. Shown in dark brown is the HYC pyritic shale member. It is thicker in the sub-basin, and it more or less corresponds to the transgressive systems tract of sequence B1. So this maximum flooding surface here can be developed as high TOC shale and pyritic shale in sub-basin depot centers, and therefore it seems to be the ideal chemical trap and should therefore be the exploration target in syngenetic models for mineralization. That means models that assume an oxidized base metal brine was exhaled into a euxinic hydrogen sulfide-rich water column, base metal sulfides precipitated and were deposited on the seafloor together with the sediment. However, there's a recent push advocated, for example, by our colleague Sam Spinks here at CSIRO or Joe Magnell in Potsdam, that the mineralization is actually diagenetic to epigenetic and represents sub-seafloor replacement of carbonate in the dolomitic siltstone. And this model now has an important implication for exploration, because it means the rocks were already buried at the time the mineralization occurred. We don't know how deeply buried. Conservative estimates would be tens to a few hundreds of meters. Importantly is that at this depth, the rocks would start to be lithified, and we can assume that this black shale would have a lower permeability than the underlying dolomitic siltstones. And also clay smears associated with this black shale where it intersects the fault would clog up the fault. And therefore, in this model, this maximum flooding surface where it is developed as a black shale would not be a chemical trap anymore. We would think it would rather be a physical trap, a seal to ascending base metal brines. So that means we don't target it as a chemical trap anymore, rather as a seal, a physical trap, and we expect the mineralization to sit beneath it in these transgressive dolomitic siltstones. So they probably have less organic carbon and pyrites than the black shale, but they still have a lot of organic carbon and black shale, and therefore they seem to be a suitable trap. They also have carbonate, which is something important for the subsea floor replacement. So I sketched in the mineralization here because at CSIRO here, we prefer the subsea floor replacement model. If you prefer the syngenetic model, that's fine too. My important point here is it is this maximum flooding surface that we need to consider when we target these kind of deposits, either because we think it is a trap or because we think it is a seal, depending on the model that you prefer. So we miss one important piece of information now. We understand the maximum flooding surface is important, but we need to know where was it actually developed as a black shale and therefore has the desired trapping or seal properties as opposed to just being a dolomitic siltstone. This means we need to create a Facies map of this time slice here, the B1 maximum flooding surface, and map out where in the basin was it a shale and where was it not a shale. So let's talk about the little map here first, A. This is a preservation map. Every area here in gray means Barney Creek Formation definitely preserved. Area in white means Barney Creek Formation not or only sporadically preserved. Area in blue means we don't know. And area in green means likely preserved, but it's a deep subsurface. This here is our Facies map now. So overlain on the reduced to pole magnetics is the layer of where the Barney Creek Formation is definitely preserved. And those red outlines here represent the sub-basin boundaries, or boundaries of known sub-basins. These white circles and these black circles are now drill cores. So those are our only source of information to create this map, our only control points. And you can already see that this is only a very low resolution map. The difference between the color is white circles means I've actually locked the drill cores, so we are very certain about it. Whereas black circles, that's what I'm actually currently working on, I have only core images to decide where's the maximum flooding surface and is it a shale or not. We can see if, or I should point out, the white lines means yes, the maximum flooding surface is developed as a shale. And if we have crossing white lines, it means this shale is thicker than 10 meters. So as assumed or expected, if the maximum flooding surface is developed as a shale, it will be mostly in sub-basin depot centers, but we can see not every sub-basin seems to have the shale developed as maximum flooding surface. So again, this is fairly low resolution, but important is the logic behind it. We know the maximum flooding surface is important for targeting, and we want to know where is it developed as a potential trap or potential seal, depending on the model we prefer. And companies exploring in this area will have confidential drill cores so they can quickly fill in this map here. So I think that's pretty neat, but it's still not quite there because we miss another piece of information, and this is we need to consider the modern day structural complexity. And luckily, Teagan did all this good work on the structural geology, which we can now integrate. So this here is a map of the southern McArthur Basin that shows us solid geology beneath cover, and it is on a group level or subgroup level. This here is a map of the Batten fault zone and adjacent areas, which is now formation scale level, and Teagan used different geophysical techniques to map out where certain lithostratigraphic units will be undercover and to understand the structural complexity. Those red circles here are again the locked drill cores, and we are integrating the stratigraphy, sedimentology, and structural geology now to construct a cross-section through this region. And it will be a north to south cross-section, complemented by a couple shorter west to east transects. We are going to look at this cross-section from the southwest towards the northeast. Again, from the southwest towards the northeast. Here's the north arrow. The cross-section is 15 times vertically exaggerated, meaning this is a 500 meters vertical scale, and this is a 5 kilometers horizontal scale. Shown in blue here are the drill cores that we've logged. We've also labeled them, and we also labeled the sub-basins here. Shown in brown is the Barney Creek Formation throughout this region. Shown in dark brown, the HYC pyritic shale member, which more or less corresponds to the transgressive systems tract of sequence B1. And therefore, more or less at the top occurs, shown here by a dashed line, the maximum flooding surface. And we have now included information from the Facies map, where is the maximum flooding surface actually developed as a black shale. So it's more than 10 meters thick here in the Glide subbasin. It is there, but less than 10 meters thick in the Myrtle subbasins, this area, but we cannot see it in any of the drill cores of the other subbasins further to the north. So again, these are all publicly available data, and this is probably low resolution, but it presents a workflow that we think is important to target these kind of deposits. So coming to the end of our presentation, we just want to briefly summarize, looking at the mineral systems model again. Teagan used different geophysical techniques to identify different faults beneath cover, and she recognized where subbasins are and was able to distinguish two different types of subbasins. I then combined Facies analysis, sequence stratigraphy, and the structural geology work from Teagan to develop a conceptual targeting concept based on the trap. And some things that we have not talked about much, but it's also really important for exploration, is the location of the metal source. So for example, if those enormously thick volcanics beneath McArthur River and Tina that Teagan modeled are in fact the metal source, then you may want to be careful picking tenements beyond the outer limits of this pile of volcanics. However, if you think it was mostly felsic components of the basement or silicic units in the Tawallah Group derived from those felsic components, as Josephine just published in geology, then you have to look, where is this potential metal source and how does it relate to the structures Teagan talked about and the sedimentology and stratigraphy that I talked about. So at the end, if you're interested in some of the works that we have published, some papers are out already. Other papers are currently in press in economic geology, for example, the one here by Sam about the subsea floor replacement model, and other papers will be submitted soon or are currently in review. More importantly, some of the works that we are currently doing is stratigraphic forward modeling, as it is done in the petroleum world. So we want to basically model where does shale, where does organic carbon and pyrite occur between our drill cores as control points. We want to integrate this with fluid flow modeling. So we want to understand which structural configuration do we need, cross faults and angle of faults, dips of faults, and so on, to help bring mineralizing fluids up. And we really want to integrate those two instead of just having them on different software platforms. So thank you very much for your attention. We are very happy to try to answer any questions you may have. And I will change the microphone and speaker setting now.
Okay, as I'm saying, I would like to thank Marcus and Teagan for this really nice overview on the McArthur Basin. And I highlight how important are the multidisciplinary projects and their high relevance to better targeting deposits. I think we are already questions. Our first question is from Josephine. Teagan, do you want to unmute yourself and ask the question?
Yeah, hi, can you hear me?
Yes.
Yeah, hi, Marcus and Teagan. I'm happy to see you again and thank you for your talk. I have a question for Teagan concerning this large felsic body that you discovered at the interface between the basin and the basement. I was just wondering if as you take, I assume that you take for the basement the same density for your models for all the basements, and I was just wondering if it's possible to know if the felsic body that you discovered was part of the basin, like intrusion in the sedimentary sequence or if it could correspond to a felsic rich zone in the basement.
Yeah, as you mentioned, the basement is pretty much all the same density across all the models, and we do need this low density zone, I guess, to reconcile that low gravity anomaly that we observe. With this kind of modeling, there is some uncertainty, especially at that depth in geometry of these structures. So I modeled that body within the basement. That doesn't mean that
alternate interpretations aren't possible. So it could potentially be a little bit shallower if that granite or that felsic intrusive was shallower. It's likely to be potentially a little bit smaller than what I modelled. I guess there's no yes or no to your answer. I put it as something in the basement. There is sort of a sort of zone of poor reflectivity in the seismic, so it's sort of difficult to I guess pinpoint its location from that as well. So that there's definitely you need something there to reconcile the geophysics. I think it's in the basement based on my interpretations, but yeah, it could potentially be an intrusive within the Tawallah Group as well. That is possible.
Are there felsic intrusives known elsewhere in the Tawallah Group that could be equivalent?
Yeah, there are some rhyolites in sort of the upper part of the Tawallah Group.
Let's say upper part, yeah.
But they're located a little bit more to the west, and they're not particularly regionally extensive.
If I could just follow up on this, because we're on the same theme, also on the theme of when. So you've identified east-west forming faults, and I'm trying to find, you have an event of east-west shortening earlier on in the history of the basin or the sub-basin. But I think when you're getting to the 1645 age, which I think I'm a bit more familiar with, which might be deposition of the McArthur Group, you're talking about north-south extinction. So so when do you think these east-west faults are forming then?
I think because we're seeing potential thickening of the Tawallah Group against these east-west faults, I think they were an inherited structure that that existed at the time of the deposition of the Tawallah Group and were reactivated at the point the McArthur Group was deposited. So potentially whether that's a structure that is again being inherited from the basement, I'm not sort of can't really determine that. But I think definitely they were active during deposition of the Tawallah Group and have been reactivated during McArthur time.
Okay. Filipa?
Sorry, I'm muted. We have another question from, let me see, Alexis. Do you want to unmute yourself and do the question?
I'm just trying to unmute him right now. Might not be able to.
Okay, I can read the
okay,
question.
Can you hear me?
Yes, there we are.
Yes.
Yes. Okay. Thank you for that those presentation. And my question is just to know about mineralization. Is those deposits directly on trapped on black shales, or are there on the contact between black shales faults and bituminous dolostone?
So, yeah, at McArthur River, there is a 25-meter thick black shale above the stratigraphically uppermost ore body, which is ore body number 8. So it should be in this transgressive systems tract. When you look at the actual ore samples, you will see that little shale laminae are not mineralized, which would be important probably thinking about permeability, contrasts, and so on. At Tina, the known information are fairly little. There's one report from the people at Tech saying the most organic carbon-rich interval is above the mineralization. There's one paper by Joe Magnus suggesting the maximum flooding surface is 100 to 200 meters above the uppermost ore bodies. This would make, if this is true, then this would make this transgressive systems tract in this sub-basin extremely thick, which I think is rather unlikely. And I suspect it is lower, closer to the ore bodies. But there is no published, I'm not aware of any well logs, and I wasn't able to look at any drill core to further evaluate this. Does this more or less answer your question?
Okay. Thank you for your response. And this is just because my question is to know if in that in this deposit are there like a petroleum systems? Do you know about are there you are black shales and also dollarstones? Like dollarstone can be as reservoir rocks, and then you can have a system to have hydrocarbon flow on the reservoir, and which can be which can trap your mineralizations.
So yeah, it's these deposits at McArthur River and Tina. There's no oil, so dollar stones are very tight, impermeable, and have a very low porosity and permeability. They would not be a reservoir. The question is very interesting, however, because the Barney Creek Formation itself did not pass the oil window in many locations. We've got hundreds of rocky val data with thermal maturity information, and it's usually kind of in the oil to gas window. So the Barney Creek Formation itself could actually be an unconventional gas play. The petroleum aspect becomes more important on the Queensland side. There's one deposit where this is part of the mineral system. But to answer your question, no, not in the southern McArthur Basin.
I think we're always going to be wondering about the roles that hydrocarbons play in all of these systems. I think that's a growing avenue of research and interest,
Yes,
right?
yes, and actually biomarker studies have been published from McArthur River, suggesting various things, high temperatures, for example, 400 degrees as mineralizing fluids and so on. But I don't want to go into the detail, but there's one paper in review currently that basically says those biomarkers are all migrated and not syngenetic. So making all the previous conclusions obsolete. But bringing this organic geochemistry world towards these kind of deposits, I think is very important if the maturity is low enough and allows it.
Great. Our next question is coming in from Belinda Smith. Belinda, do you want to go ahead and ask your question?
Yeah, thanks for that, Teagan and Marcus. I'm just sort of like looking at the images that you've done. I know that you've published a lot of papers. I was just wondering if those 3D images are going to be available in some sort of software package in a way that enables people to sort of zoom in and actually have a look at some of those sections in greater detail.
You mean, hi Belinda, first of all. By the way, I got the photos now, the core images. You talk about Teagan's images?
Well, both of you actually. As I said, I'm just sort of looking at some good images that both of you have, and obviously it's something that'd be great to zoom in on and have a closer look at.
Well, the answer is yes, they will be made available through the NTGS, hopefully in the next month or so. We're just sort of wrapping up a few sort of final little details with all the data sets I've provided for this work. Hopefully they should be published through NTGS shortly.
Yeah, and the kind of pseudo 3D cross section that we showed at the end is part of a manuscript that we will submit soon. And I will at least put it in as a PDF figure so that people can zoom in as much as they want. But this is basically, this was done in Illustrator after providing a skeleton in GoCat. So it's not really a shapefile or anything that you could load into 3D modeling software.
Okay, thank you very much. We have another question from Joe Magnol. He appreciates this talk and said it's a fantastic data set that you have presented. And the question is, if pyrite is suggested as a source of sulfur, do you have any ideas for where the iron from pyrite is going? It's perhaps worth considering that the maximum concentration of zinc and lead sulfides often exceeds the maximum concentration of pyrite in these sequences. which implies the reduced sulfur cannot be all coming from pre-existing pyrite.
Yeah, thanks, Joe. That's also what I take from your paper, right? I don't know where the sulfur. I don't know a potential second source of sulfur, basically. If you have an idea, let us know. My idea is if the trap is a pyritic rock, then surely this pyrite must have been one part of the sulfur source, an additional sulfur source. I personally don't know. It would be interesting to hear your thoughts on that.
Joe, do you have any thoughts on that? I'm going to unmute you right now if you would like to keep this part of the conversation going.
Okay.
In which case, in case I can't get Joe to unmute, then actually Dave Thomas had a two-part question, and I think he's also dropped out or left, but he may have missed it, but in case you didn't touch on it. But has there been any work on identifying the effects of oxidized metal-bearing fluids, such as alteration and isotopic changes when they migrated upwards along the presumed fault-controlled conduits? Would these have been broadly distributed fault zone fluid conduits, or are they relatively narrow fault conduits that with discrete describing that have discrete?
Yeah, we cannot answer this question in detail. Coates did alteration work, which I can refer to. We did not work on potential alteration halos, but there are a couple of interesting papers by Coates I can refer him to. Including isotopic work, carbon-oxygen isotope work, as well as potassic alteration and things like this.
Yeah, I can follow up on that. I know that Kurt Kaiser and I guess it was Paul Polito in the early 2000s, they did a lot of work on the chlorites and the illites in the McArthur Basin, basically speculating again that they called for mafic volcanics underlying the McArthur Group to be the hosts. I mean, to be the sources of the metals in that case, right?
Yeah, that's right. They published at least two very interesting papers. I'm aware of one from the Queensland side and one from the McArthur Basin, where they basically identified oxygenic minerals to understand which siliciclastic units of the Tawallah Group, of the lower basin fill, may have been aquifers at this time. So this really interesting work that I like. They basically say, even if today this seems to be an impermeable rock, they dated when the oxygenic minerals form, that they basically clog up the pore space and identified that those rocks would have been permeable and would have been aquifers at the time the mineral system was active.
Okay, thank you. Marcus, we have a thought from Joe. He has some micro issues, but he writes something about the sulfur source. Some of the models imply that oxidized sulfur is transported in the hydrothermal fluid. So this would be one option.
Yeah, that's a good point, Joe. I think we need to look where that sulfate, right, eventually would come from. So we do have some sulfate-bearing units in the lower part of the stratigraphy. I just showed this one rock photo from the Myrtle Shale. There's also sulfate in the what's it called, Malapanya Formation, which is more or less at the base, together with the Masterson sandstone of the McArthur Group. So maybe this is where sulfate could have been picked up on. How the sulfate is transported together in the fluid with the metals, that's not my field of science, and how this would affect basically the solubility of metals in the fluid.
Okay, I think I would like to ask a question then to Marcus. I think it's just more of a you know, for those of us, I know I've come from a little bit more of a sedimentology background. I would like to for your stratigraphic modeling, have you been able to use any other data sets to sort of reconcile your interpretations at the scale? I mean, when you were obviously what Teagan was talking about is a much bigger scale, but is there anything else that that you're using then that will help with your stratigraphic model?
You mean the modeling software?
Yeah.
Yeah, that's something we start. So the only control points you will have are drill cores. So you would basically take some of them and includes information from them in your modeling, and you would leave out other drill cores to ground truth your modeling. So if your model is able to produce those other drill cores that you have not included in it, then you can get some certainty about it actually seems to work. And this is something that we will be doing soon.
All right, and we have a question coming in from the YouTube from Jonathan King, who is asking if you can comment at all on your basin modeling efforts towards MVT mineralization in the Leonard's Shelf.
Yeah, I'm not quite sure how I understand the question. I would just broadly say the techniques we used are very applicable there. If you look at carbonate-hosted mineralization from a sequence stratigraphic point of view, you're probably more interested in the high stand kind of system tract instead of the transgressive system tract. We have not worked there at all, but the same techniques could be used there. And you just need to find the other ingredients that you think are important, right? For example, a permeable carbonate with a facies instead of a pyritic shale or siltstone or something like this. I don't know if you want to add something to it.
Okay, I think I'd like to just revisit one more idea, which was the burial depth of the McArthur Group. You know, it's crazy to believe that something has sat around on the surface of Earth for nearly 1.6 to 1.5 billion years, and it's barely been past the oil window. And I think
that's really exciting, right? And that's why the Bonnie Creek Formation is host to some of the oldest indigenous biomarkers in the world. So a lot of biogeochemical cycle work in deep time actually comes from the Bonnie Creek Formation. And just recently, the only paper that goes even deeper into the Volga Formation now shows that those are the oldest biomarkers. But yeah, I'm just amazed when you look at the rocks, how fresh they are. And when you cut some of these bituminous siltstones and shales, you actually smell the gas.
Life finds a way, I suppose.
Yeah, it's really exciting, yeah.
Filipa?
Yes, I think that's all. We don't have more questions. I would like to thank you. It's a really informative talk. And thank you again, Marcus and Teagan, for this talk.
Thank you both for inviting us to share our research, and we hope that people found it interesting to some degree. Thanks very much for having us.
Yeah.
It was interesting to a very high degree, Marcus. Thank you so much for your presentation. And thanks as well for the high quality work that CSIRO continues to produce and share with us on ODH. So with that, I'd like to say thank you to all of you. To some of you, good night. To all the rest of you, good morning. Have a great day.
Okay, thank you. Bye.